Hello, I am Professor S. Sankaran in the Department of Metallurgical and Materials Engineering. I just want to very basic points which you all might have already studied, just to recall this. Physical quantities that transform with the coordinate axis in a manner of equation, whatever we have just seen, one coordinate to other, okay, are called the tensors of second rank. Okay, the physical quantities. What are the physical quantities we measured? We looked at stress. Okay, that's the physical quantities. So the physical quantities such as stress, strain, okay, that transform with the coordinate axis in a manner like what we have. They are called tensors of the second rank. Okay, so the stress, strain, and many other physical quantities are the second rank tensors. Very important. So you keep that in mind. The one good thing is about this is, so once you see that stress can be treated as second rank tensors, then there is a lot more avenue to do mathematical manipulation. That's the idea, right? All the tensor quantities, all tensor manipulation you can bring in and then try to see how much clarity we can bring in, because such a complex quantity, it's not like in a vector, like which requires only 3 components to describe, but once it moves to the tensor form, it is a little more complicated. So a scalar quantity which remains unchanged with the transformation of axis requires only a single number for its specification, and they are tensor of 0 rank. Okay, so any scalar quantity is not going to change. They are going to remain unchanged for any transformation of coordinates. Okay, so they are tensors of 0 rank. Just I mentioned, vector quantities requires only 3 components for their specification. So they are tensors of a first rank. So a vector is tensors of first rank, and the stress is tensors of second rank. So this is important. So the number of components required to specify a quantity is 3 to the power n, where n is the rank of the tensor. And we are going to see in few classes the elastic constant that relates stress with the strain in an elastic solid is a 4th rank tensor with 81 components in the general case. Okay. So we use elastic constants, Young's modulus, right? So that relates the stress and strain for a pure elastic material, as it's a 4th rank tensor. That means 3 to the power 4, which is 81 components are required to specify the state of stress clearly. Don't describe the state of stress, whatever. So, but we will be seeing this when we go to a specific cubic system, how this elastic constants are evaluated, right? So stress is a second rank tensor. The components of the stress tensor can be written as like this. So we can write sigma ij, it's a tensorial representation, is equal to mod of sigma 1, sigma 12, sigma 13, and sigma 21, sigma 22, sigma 23, sigma 31, sigma 32, sigma 33. Or it can be simply a sigma x, tau xy, tau xz, and so on. So, so once it is in the form of the matrix, then it is easy for us to relate this with some other properties as well. For example, the first invariant of this matrix is I1. We were talking about 3 invariants, right? So the first invariant is I1 is what? I1 will be sigma x plus sigma y plus sigma z, right? So I2 is what is summation of principal minors, right? For example, if you take what is principal minors? So if you take this, so it will be sigma y tau yz, tau zy, sigma z plus so on. It will keep on going like that, right. So, the I3 will be, see the I3 will be the solution of the entire determinant, right. So, that will be the, these are all the quantities we can relate. We have already seen that, so I am not going to repeat it. I have already shown what are the invariants in the 2-3 slides before. So, all that I want to emphasize here is stress is a tensor of rank 2 and it can be written like this. Okay. So, this is some of the basic idea I want to just flash it and then move around. So, again coming back to this Mohr circle of 2 dimensions we have seen, but this is going to be a 3 dimension now. So, this is not 2, this is 3. Okay. So, the Mohr circle also can be visualized in 3 dimension. So, what you are seeing in this Mohr circle is how a triaxial state of stress defined by the 3 principal stresses can be represented by 3 Mohr circles. So, what is that we are seeing? So, this is the member which is subjected to triaxial state of stress. That means 2 normal stress of equal magnitude. The third one is in a compression mode, these 2 are in a tension mode. So, 3-dimensional state of stress is plotted in Mohr circle. So, what we are seeing here is you have sigma 1, that is the highest principal stress, and sigma 2 is here, and sigma 3 is completely compression. Sigma 3 is compression, sigma 2 is tension, sigma 1 is tension. And talking about shear stress, the tau 2 is highest, and this is a tau 1, and this is tau 3. Okay. So, tau 3 and tau 1 and tau. So, any combination of stresses can be brought into this a simple representation, a graphical representation. That is the beauty of this representing the Mohr circle, right. So, that is how you can just make use of them. So, to take some few examples, this uniaxial tension, and you see that there is only one axis where sigma 1 is acting. So, this is how it is represented. So, it is very simple. If you have sigma 1, so the sigma 1 is the maximum, and this is the sigma 1 by 2, that is a maximum shear stress, and sigma 2 and sigma 3 will be 0, okay, if it is a uniaxial tension. At the same opposite, uniaxial compression, so it comes to a complete negative axis, sigma 3. So, and then this is a max, and sigma 1 and sigma 2 is equal to 0. So, this is this way of representing. And you can now represent biaxial tension and triaxial tension. So, biaxial tension is this is an element of equal magnitude, sigma 1 and sigma 2. So, you have this sigma 3 is 0 here. So, sigma, you can see this is the maximum, and then this is sigma 2 in tension, and this is tau 3 maximum and tau 1 maximum, and this is tau 2 maximum. Okay, shear stress maximum is here. This is tau 1 and tau 3. Okay. So, what is that? Even though it is sigma 3 is 0, but sigma tau 3 is not 0. So, this is how you have to remember, right. Similarly, for triaxial tension, so this is an element where it is subjected to triaxial tension. So, sigma 2 and sigma 3, they are equal in magnitude. So, sigma 1 is the highest here, and this is sigma 2 and sigma 3, and this is a tau max. Okay, and uniaxial tension plus biaxial compression. So, uniaxial tension this direction, biaxial compression in two orthogonal direction. So, how it is represented? So, you see that sigma 1 again the highest, and sigma 2 and sigma 3 are equal, but in compression. So, you have tau max is here, which is tau 2 is equal to tau 3 is equal to tau max. So, the what you can appreciate by looking at all these examples is any combination of stress, okay, can be visualized. You can just resolve this normal stress versus shear stress, and also as a function of any angle orientation, right? You can just easily represent this. That is why it is useful, right? We can just look at the it's basically a representation, but instead of looking at all these complex equations, if you can just put this in one graph, then it is easy to visualize. So, that is an advantage, right? Okay, that is about this Mohr circle, and so far we have just discussed about the description of stress. Now, I want to move on to description of strain. Okay, so again it will be a little more detailed, but you will realize that as we move along in the course, these are all very important, but people normally tend to ignore this small details. So, it is better to spend some time on this and then have a complete grip and then get into the subject. So, like strain, like stress, strain is related to change in dimensions and shape of a material. The most elementary definition of strain is when the deformation is along one axis. So, like this, you have the normal component and which is being pulled in both direction in a or one direction, in one axis in both directions, right? And strain is given a very simple definition. Strain is equal to change in length by original length. In the beginning also we have just written average strain. We talked about average strain, right? And here we are talking about a strain at a description of a strain at a point. Okay. Here also we are making a very simple introduction. We are not giving any specific coordinates or the point, but just a general description. Then we will get into the details. Okay. So, when a material is stretched, the change in length and the strain are positive. When it is compressed, the change in length and the strain are negative. So, you can do when you say change in length, it could be uniaxial tension or compression. Both operation involve the change in the shape, right? So, it could be a positive strain or it could be a negative strain. So, we can this confirms with the signs of stresses which would accompany these strains. Tensile stresses being positive and compressive stresses are negative. These are conventional way of putting it. And as I just mentioned, this is this definition refers what are called normal strains, right? Which change the dimensions of a material but not its shape. In other words, angle do not change, very important. So, when you say normal strain, we are not talking about angle, okay. So, it changes the dimensions of a material but not its shape, okay. On the other hand, there are normal strains along three mutually perpendicular axes. So, similar to stress, we also have the normal strain along the three mutually perpendicular axes. The moment you bring this kind of a change in this, what is that changing. Here it is again a shear stress notation. So, the shear stress brings what change into this basic member. So, it gives a angular change phi by 2, okay, here and here with respect to this line and with respect to this line, there is an angle change. So, when there is by contrast, strains which involve no length changes, but which do change angles are known as shear strains. Okay. So, normal strain and shear strain. Okay. These are all very subtle definitions, but it is useful if you pay some attention what are the details involved, because these things you can relate later on, for example, if you say deformation. So, what causes deformation? What type of, is it just a simple length change, or whether it is a slip, or we will use a lot of terms, right? So, these small details only bring in clarity later. So, that is why we are paying attention to this. And for normal strains, the usual symbol is epsilon. The same system of subscripts is used as for stresses with respect to x, y, z axis. We have strains epsilon xx, epsilon yy, and epsilon zz. With the stresses, the first subscript giving the normal to the plane which is being displaced, and the second subscript indicates the direction of displacement, similar to what we have described in the stresses. Strain also have two subscripts to describe. And since the subscripts are always repeated, we sometimes just use single subscript. Conventionally, the symbol for shear stress is gamma, and the same subscripting system gives rise to strains such as gamma xy, gamma yz, gamma zx. So, now we are looking at shear stress. Sorry, not shear stress, it is a strain. We are discussing about strain. Sorry, it is strain. There is a typo. Shear strain here. Okay. Other quantities that are associated with the strain are displacements. Okay. So, what are displacements? So, we need some time to demonstrate this. These are simply the distance moved by any point of the material. Usually, the displacements in the x, y, z directions are denoted respectively by u, v, w. When a strain is present, the displacement must vary from point to point. It is easy to see that normal strains are given by epsilon xx is equal to dou u by dou x, epsilon yy is equal to dou v by dou y, epsilon xx is equal to dou w by dou x. This is again a typo here, epsilon zz, right. So, the displacements are for a normal strains are given like this. In these cases, the strains are always small. This enables us to use simple theory, right. In this context, small means that the square of the strain is negligible in comparison to the strain itself. For example, epsilon square is far less than the epsilon. Okay, so that is the idea. In general, the action of stresses will cause material to change its volume. Only the normal stresses are associated with the volume strain. We define volumetric strain E as change in volume divided by original volume. So, we are bringing now little more details as compared to normal strain, or we will later on we will also see that engineering strain. We will come to that, but then even before going into other details, normal strains, now we are talking about volumetric strain, right. The volumetric strain is simply related to the normal strain. Consider the rectangular solid illustrated. The original shape is on the left hand side and the deformed shape is on the right hand side. So, the volume of the original volume is given by the V naught. del x, del y and del z. So, this descriptions I will go with some little more illustrations. I do not want to overload today. I will just stop here. We will come out with some more descriptors, and then we will continue the discussion on describing the strain in much more detail with a little simple mathematical formulas, and we will also bring some clarity in nomenclatures, right? For example, normal strain. We were talking about an average strain, okay? That what is that normal strain, then what is the shear strain we know, then now volumetric strain we are talking about. So, we will bring in lot more clarity once we bring some geometry and then describe in terms of some basic equations, then that clarity also will come, because please remember, ultimately we will be experimentally measuring only the strain, right? So, I said that stress cannot be physically measured. So, it is better to bring in little more clarity in this domain before we get into other relations, right? So, that is the purpose of this introduction and fundamentals, and we are spending too much time on this because it will give lot more clarity and confidence as you move along, okay? So, we will continue in the next class. Bye.